Hello all, welcome back. In the last tutorial on the OLED display, we have completed the initialization part of OLED, and in this video we will actually display some information on the OLED. So as you remember, this is where we stopped. We finished the initialization and we went to a state where every pixel on the OLED display was turned on. Okay, so we'll start from this point. Now, instead of turning on all the pixels, we actually want to display some information. So I am commenting out these states, and instead of going to this state, we will create a new state. So the first thing that you need to do to display something on OLED is again to send some commands, and in this command you will basically tell in which page the data should be displayed. So remember, there are 4 pages, 0, 1, 2, 3. So you need to specify on which page the data should be displayed, and you should also specify starting from which column the data should be displayed. Again, there are 128 columns, so you can specify what is the starting location for displaying the data. Okay, so I'm creating a new state here called, let me call it page address, and so in this state again you have to send some command through the SPI interface. So the command is hex22, then SPI load data, take P1, and OLED command data is 0 because this is a command, and if SPI done, we'll make load data back to 0. We'll go to, as usual actually, wait SPI so that the SPI controller sees SPI done signal, not SPI done signal. He deasserts SPI done signals. And next state, I will call it page area 1. So here I am sending the command 22, which basically says this is a command for specifying the page address. Now in the next state, I am actually going to specify the page address. Okay, so begin SPI data, the page address which you want to display. So we'll create a new variable, new register to store this information, which page should be used for displaying. I'm simply writing current page here. I will declare current page, and when we reset, let's make current page as 0 because initially we want to display starting from the first page, first line. Now there are 3 pages, so I will have to count 0, 1, 2, 3. So basically I need 2 bits to specify the page number, whether it is 0, 1, 2 or 3. Okay, so when we come here first time, current page will be 0, which is the start page address. Then we'll say SPI load data is 1. Actually I can simply copy paste this. If SPI done, 0, hit SPI and we will increment the current page so that next time, once we finish this page, next time when I go to the same state, current page is 1 more than this, and I will move to the next state called page address 2. Okay, so in this stage I need to specify till what page I want to display. Again, you have to read the data sheet little bit. So we are using a particular mode called the page mode of OLED display, where you will have to specify the start address of the page from where you want to display and the end address of the page till which you want to display. And in the mode that we are using, you can at a given point of time can display only on one page. Okay, so if you want to display on two different pages, you have to configure the start page address twice actually. So page address 2 and again current page, but remember this current page is one more than this one, so if it is 0 here, it will be 1 here. Load is 1, if SPI done, load data is 0, wait SPI. Okay, so we don't need this one. Okay, so next state, as I mentioned before, you need to specify the page number. Also, you need to specify from which column you need to start the display. So I'm going to a state called column address state, and again it might look very similar, maybe something like this. Column address, so the command is 10 and this command actually embeds two information. It also tells this is a command for specifying column address, and this 0 at the end is also specifying I want to start displaying from column address 0. So remember, this is a 8-bit data, so 1 bit is used for specifying this is a column address command, and remaining bits are used for specifying from which column I want to display. Since there are only 128 columns, you need 7 bits to tell that information. Okay, so all remaining bits are 0, that means I want to display starting from column 0. So load data 1, this is also command data, we already made it 0, so either you can keep it or remove it. SPI done, load is 0, state wait SPI, and from here I will go to the done state. I specified the pages, I specified the column. The only thing now left is the actual sending of data. Then that data will be displayed on the screen. So the idea is again to use a producer consumer model. I will write one more module, and that module will actually give me the data which has to be displayed on OLED. Okay, so that's the idea, so that I have a better control on what should be displayed on OLED. So we'll write one more module. That module will ask the OLED controller to display something. He will also tell what should be displayed. Then the OLED controller just displays the data. So that's the idea I'm going to use. So my assumption is there is a signal called send data valid, which will be coming from some other module, and this signal will become high whenever that modules want to send some data. Okay, send data valid. Okay, let's start like this. When the signal is high, we will go to so-called the send data state. Okay, so let's come to the send data state. Okay, now here things are a little bit complicated. So remember from our discussion on how characters are displayed. Okay, so remember, if you want to display a character, we are assuming this is an 8 by 8 array. And for example, if you want to display A, you have to send this much information to the OLED controller. Now, depending upon the character, okay, the data that you want to send is different. Now, one way to do this is to make a small memory inside FPGA, inside the PL part, and in that memory, you will pre-store all these bit patterns which has to be sent to display a particular character. And so this memory will have some address bus going in, and it will have some data bus coming out. So this is more like a ROM, read-only memory. Now, to the address bus, I will give the ASCII code corresponding to the character which I want to display. For example, if I want to display A, I will send the ASCII code for A as the address to this memory, and that memory will provide me this entire bit pattern. Okay, then from that bit pattern, I will take one byte at a time and send it to the OLED display. So remember, you have to send 8 column, each one is 8 byte. Each one is 8 bit, 1 byte. So you will have to send 8 bytes to display a single character, and SPI can send only 1 byte at a time. So you have to do 8 SPI transactions to send the information for a complete character. So first thing I am going to do is building this small memory which will store the bit pattern for every character that I want to display. So I am planning to display only the ASCII character. So there are only 127 character, and let's go ahead and build that model. So I am calling it char ROM. Let that be the name of the memory. So create design source. I'm just calling it to create file char rom.v. Okay. Finish. So this is my ROM, which is storing all this bit pattern. So it's a ROM, so he takes the address as an input. Now remember, the address is the ASCII code for the character which I want to display, and original ASCII code, it is only 7 bits, 7-bit ASCII code. And let me call this the address, and he gives the corresponding bit pattern as output. So what should be the width? Each character is encoded using 8 bytes. So the output should be 63 down to 0, and let me call it data. Okay, so this is how it looks like from outside. So inside I have to create a memory which is basically a 2-dimensional array in Vivado, so reg. And again, remember, each location is storing the bit pattern for one character, so each location should be 64-bit wide, and this is the name of the memory. You can give whatever name you want, and the depth. Okay, so there are 128 characters in ASCII, so you can call 127 down to 0 or 0 down to 127, both are fine. So this is how you model of memory. Just declare a 2-dimensional array, but this is the syntax: reg, width, name, depth. I'm going to store the bit patterns here. Okay, for that I'm going to use the initial block, begin, end. Now you need to find out the bit pattern for every character in ASCII code, okay, which I have already found out. So I'm just copy pasting it. For example, we have A, which was 407C, okay, which you can see here actually, 407C, 4A09, 4A7C, 4000. That is this one. That is stored in memory location 65 because the ASCII code for capital A is 65. Similarly, this pattern corresponds to capital B. This corresponds to capital C, so on and so forth. Okay, so some of the initial characters cannot be displayed. There is no display for it. That's why we are storing 0 for those characters. You can refer the ASCII table. The first character that you can really display is the ASCII 33. Okay, so you can go ahead and check. So basically we have capital A to Z, small a to Z, number 0 to 9, and other characters like comma, exclamation, question mark, etc. So this is the complete memory content. Or 128 character. Now the idea is when I give a particular address, the code corresponding to that address, which is basically the ASCII code, should come out. So I will write assign data equal to memory of address. So when I place the address, immediately the corresponding data will come out, which is actually 64-bit. Fine. Okay, so I'm going to instantiate this also inside my OLED control. Okay, let's have our car ROM here. Let me call it CR, and the address will come and the data will come. Now again, my assumption is, as I said before, some other module is going to tell me which character I want to display on the OLED. Okay, so that's my assumption. So that will be coming to my OLED controller from somewhere else. So some module will give me which character I want to display. He will also tell me send data valid, I guess. Send data valid. He wants to send a data. So these two information will be coming from some other module. That's my assumption. So this is the character he wants to send. So I'm directly connecting that here. And this one, let me call char bitmap, this formal port, and I'm going to display, declare it here. It is 64-bit word. Okay. Now let's come back here. Need a comma here. Okay, so we are in this state, send data state. Okay, we came to this state because I saw somebody wants to send some data because this signal is high. At the same time, the data to be sent is coming out of this char ROM. So this is the data you want to send. But remember, this is 64-bit wide, and you can send only 8-bit at a time, 1 byte at a time through the SPI interface. Okay. So and you need to start sending from MS bit. So remember again, that is the requirement. You should send the MS byte, this one first actually, to the OLED. So basically from this char bit map, which is 64-bit, you need to choose first 8-bit, then next 8-bit, then next 8-bit, so on and so forth, and send it over the SPI data. So I'm going to call SPI data is char bit map the upper 8-bit. Okay, so we basically need a loop here because you need to send 8 bytes. And the loop, you cannot use for loop and all, unlike in our normal software programming, because if you use for loop and you are writing it in an always block, that means whatever you write in a for loop, that entire thing should happen on the same clock edge, which doesn't make sense. So what we'll have is, again, we'll have a loop variable, but we will change its value only once every clock cycle. Okay, so I'm going to have a loop variable called BiteCounter, and look at the syntax first, then I will explain. I'm writing BiteCounter times 8 minus 1 minus colon 8, and this BiteCounter I am initializing here to 8. Okay, now let's see what is actually happening. So this variable is 8. It will be a register. This register is 8, and if you put that value here, you will get 64 minus 1, which is 63. And this syntax basically means the lower index is 8 less than the upper index. Okay, so this is same as writing BiteCounter is BiteCounter times 8 minus 1 colon BiteCounter times 8 minus 1 minus 8. Okay, so same thing, but if you write like this, this is not a correct syntax in Vivado, although I don't know why it is not a correct syntax. This makes perfect sense, but basically the tool will say you are using a variable for upper as well as lower index, and this is not acceptable. So same thing, you will have to write following this syntax. Okay, so this is the upper index, and this is basically saying the lower index is less than the upper index by 8. Okay, so if it is the other way, if the upper index if the lower index is more than the upper index, you will have to say plus here, and by how much it is more. So this is the syntax. So if you want to start from ls byte and go to ms byte, this is how the syntax looks like. But in our case, we want to start from ms byte because that's the requirement for OLED, and you need to go to ls byte. So the syntax will look something like this. Okay, so after that, we'll say SPI load data is 1. And remember, till this point, this OLED DC underscore n, we always used to assign it to 0 because we were sending commands to the OLED controller. But this time, whatever you are sending, this will be stored in that internal RAM. You remember this RAM, GD RAM. Okay, so this is treated as data, not as a command. So since it is a data, this signal should be made 1. That is the requirement. Okay, now if SPI done, okay, if this data is done, what you need to do is SPI load data, we will make it 0, and we will go to our wait SPI state. After this state, we will go there, same reason. Now we need to check whether we have sent all the 8 bytes for the particular character. If we haven't sent all 8 bytes, we'll come back to the same state. If we have sent all the 8 bytes, we will go to some other state. Okay, so I'm checking this byte counter if byte counter not equal to 1, I will say I will decrement the byte counter. Byte counter is byte counter minus 1. This is basically our loop variable, and we'll come back to the same state because we haven't finished sending all 8 bytes. Now else we have finished sending all data, we'll go back to the done state. Okay, so basically this is the logic. Now we send one data, one entire character, and once we send entire character, we are coming back to done state. And again, if someone wants to send more data, he'll make this signal high. Again, we will go here and send data, so on and so forth. Now this works perfectly fine until you finish one entire row or one entire page. Once you finish one entire page, you will have to send again this page address command so that next data will be displayed on the next page or next line on the OLED display. So there should be some way to check whether I have exhausted one entire page or not. So what I'm going to do for that is each time I send some data to the OLED, I am going to use a counter and I will increment that counter. Now once the counter reaches say 128, which is the size of one full page, I will know like I have exhausted one entire page, so I will have to issue that page command again. So here, which is basically telling me he has finished sending 1 byte of data, I will put a counter. Let me call it column count or column address, something like that. Okay, so I am incrementing this counter. So each time he sends, this counter will increment. Now when I come back to the done state here, okay, along with this one send data, I will also check what is the current column address. If it is less than 128, no problem, I can keep on sending data to the same page. But if it is more or if it is equal to 128, I will have to issue the page command. Okay, so here I will put a condition, send data valid and column address not equal to 128. I will do this one. Else if column address is 128, and there is send data valid, that means there's no 128th column. I have to send the next page command. So I will say state is page ADDR. So from here I will actually come here and I will send the next page command. And remember, we have already incremented the page current page number in the previous state. So if it was 0 in the previous case, now it will be 1. So it automatically works. Okay, so we added this much. And this page counter 1, okay, we'll have to make it 8 here also, because we will go there. From there we will come and from there we will go here again. So but at some point I will have to make column address to 0, otherwise he will go there and he comes back, he will still see again column address is 128, so it is stuck in that loop. So here what I will do is I will make this column address to 0, so that after he configures the page address, when he comes back here, this condition is false, this condition is true, so he goes to send data. Fine. Now any other issue remaining? Most of the problem take care, I guess. Yeah, one thing that we missed is the handshaking with the other module. So remember I told like some other module will tell me he wants to send some data, and we have to tell that module like I have finished sending data once we finish sending it. Okay, so we need that handshaking signal. So where are we done here? So here we are going back to done because we have finished sending the entire data. So I'm making a new signal send done, and this is the handshaking signal which is going to the guy who is giving me data. So send done. Let me again initialize it to 0. Let reset, and in this state I'm making it 1. I'm going to done state, and in done state we should make it back to 0, otherwise the other guy, he will keep on seeing it. Okay, now my assumption is the other module, he is also running at the same clock frequency. So if I make it 1 here and I go to done, so we will come here in the next clock, and by the time I come here he will see this signal is high, he will make his send data valid low. But the problem is that signal I will see only in the next clock. Okay, so the problem is when I come back to done state here, I will again see the signal is high, I will send the same character once again. So to avoid it, what you can do is instead of directly going to done, maybe you can go to a wait state and wait for 1 clock, so that the other module he sees send done is high and he deasserts it. That is one way of doing it. Or here you can put a condition and send done is 0, not send done. Okay, so basically when we come back to done state, he will see send done is high, so he won't go here, and here also send done will be high, so he won't go here either. But on this clock we will make it 0. So in the next clock, if send data valid becomes high again, he will see it and he will work properly. Okay, so always keep this in mind, the handshaking signal. When two modules are doing handshaking, even if you make a signal high, the other module will see it only in the next clock. So only in the next clock he will deassert his valid signal. Okay, so you have to wait 1 more clock before checking that valid signal. Otherwise you will see the same valid signal twice and you will be sending same data twice, which could be problematic, which is problematic actually always. Okay, now we have a lot of errors here. We have to correct all of them. So let's start declaring. We need to start declaring from page address 1, page address 2. Page address 19, page address 1, 20, page address 2, 21. Column address address 22. Here I think this is not declared. Now remember, this signal goes up to 128, so we need to initialize it also somewhere. So let's initialize it here. And 128, that means you need 8-bit. Using 127, it can go only till 7 bits. It can go only till 127, so we need 8-bit. Okay, 7 down to 0. Column address. Now send data is not declared, BiteCounter is not declared. Okay, send data T23 and byte address we need till 8, so it should be 4-bit. And should be initialized, but I guess it is initialized here anyway, so it is not byte address, byte count. Column address, okay, so spelling mistake, column addr. Okay, now all errors have vanished. Okay, so we have 23 state. That means I need 5 bits for states and next state. It is already 5 bits, so it is perfectly fine. Yeah, so we have almost finished the code for controller. Now the thing that is remaining is the actual module, which is going to give me the data which has to be sent over the SPI. Okay, so that module I am writing as my topmost module, and that module will basically instantiate my OLED controller inside that. Okay, so that's what my plan. So I am taking a new file and I'm calling it top.v. So my plan is to instantiate my OLED controller inside that top module and generate these signals also. Okay, so I'm copying this top and instantiating it here. Let's call it OC clock reset. Okay, clock and reset, they are coming from external world, so I can connect them directly. And all these OLED signals, they are also coming from external world, so I will directly connect them to the external pins. These signals are generated within this top module, so we'll see how to generate them. So other signals, actually I can directly copy paste from here, and they should be all wire type this time because they are connected to the output ports of a module. Okay, they should be all wire type. And this Fine. Okay. Now first thing I'm going to declare is the string that I want to display on the OLED controller. So I'm just declaring local param my string. Let's display hello world. Now if you write like this in Verilog, what is going to happen is, okay, so he will make a small memory inside the FPGA, and that memory will be filled with the ASCII code corresponding to each of this character here. Okay, so again, this is not like our software. This information is not stored in RAM or something. So using LUTs and flip-flops, he will create a memory, and inside that memory he will automatically store the ASCII code corresponding to each of this character, because you wrote it like a string. Okay, now what we need to do, we need to take one character from this string at a time and give it to the OLED controller. Okay, at a time we will take one character from here, we will give it to send data, and we will make send valid high, and we will wait for send done. So we will keep on doing it until we send this entire string. So again, we are going to write a state machine because I want to send one character at a time, one after the other. So again, a state machine we need. So always at post such clock in if reset begin end. So let me call the state as the idle state, else begin end, and we are in idle state first in case. Okay, so we are going to send the data. So first thing I need to send is this H first. Okay, I will start from H, then E, then L, so that it displays in that order. So where this character should be sent, it should be sent to this one, send data. So I'm again declaring this send data, and remember this was 7-bit wide, so 6 down to 0. Send data. So here there is a small catch. Here I wrote it 7 because as per the original ASCII specification, they are 7-bit. But currently, if you declare a string like this, each character here internally, he's going to store using 8-bit, because all the modern system characters are 8-bit. Okay, so let me declare it 8-bit, and I am connecting it to a port which is only 7-bit. But that is not problematic. He will connect only the lower 7 bits coming from here to the 7 bits here. So the uppermost bit will not be connected. It will be ignored, but that will work perfectly fine because the ASCII code for every character here is using 7 bits, 7 valid, and the 8th bit will be always 0. So this makes sense. This is perfectly fine. So I'll say, like, again, send data is okay, similar to our character ROM. Same issue here. I have a string. I need to take one character at a time. That means you need some kind of loop control variable to do it. Okay, so same syntax. So we'll say my string of, we'll use a variable called BiteCounter. BiteCounter times 8 minus 1 minus colon 8. So BiteCounter, we will initialize it with whatever is the size of the string. So the string is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So let me declare it directly. Local param string length 11, and I will just use that here, or you can directly write 11 here. Why I'm writing here? Because later if I want to change the string, I can change the string here and I can just update the size here. Otherwise I have to each time come here and change the size here. There is no operator like strlen, like the C, to directly find the string length. You have to manually calculate it and store that information here, and again inside the FPGA this information will be stored as a constant in lets and flip-flops, or using wires directly connected to VCC and ground, or whatever the implementation tool prefers. But syntactically, this is how you should write. Send data my string byte counter, which is 11 first times 8 minus 1 minus 8. So basically, take the upper 8 bits and we'll make send data valid is one tick B1. So this one we will connect here. Send data is here. So this is also reg type, reg send data valid. We will initialize it to 0 here. Okay, byte counter we need to declare. So depending upon the size of the string, how much will be the size of byte counter will change. Currently it is 11. Okay, so you need only 4-bit, but later if I put a big string I will have to keep on changing the size. So one way, easiest way, is to declare it as integer type byte counter. Now integer is usually 32-bit, you know, but when you implement your design, Vivado will automatically find out what is the largest value going to this variable. So he will not always use 32-bit. If you are using sizes less than 32, say you are using 10 bits, he will use only 4 bits for byte counter. Remaining bits will be optimized away automatically, so you don't have to worry about it. You can still declare it as integer type. But if the size is more than the size of the integer, which is 2 to the power of 31 minus 1, he will give you a warning like the size is more than the size of integer. Then you have to declare the appropriate size here. But I don't think we will ever have a case where the string size is more than the size of what an integer can store. So this is perfectly fine for the time being. Okay, send data valid, I made 1. Then I am going to the next state, and let me call it the send state. And in send state, basically I am waiting for the OLED controller to say he has finished sending. So this send done, we'll declare it again wire type. He is waiting for this signal to go high. Okay, and when that signal goes high, we will make this signal low. This is the handshaking I was discussing, and this is the precise reason we put this condition here. Okay, so he is making send on high. He will see it only on next clock, and only on next clock he will make this signal low. Okay, so if you don't have this condition, our OLED controller will see send data valid is still high, so he will send the same character once again. So that's why, to prevent that, we added this condition. Okay, so this signal we made 0. This byte counter we will decrement it by 1. Similar logic here also. And again, same logic. If byte counter is not equal to 1, that means we haven't sent the entire string. I will go back to idle state. Else, if byte counter is 1, Okay, again you have to think why it is 1 not 0. Okay, on this clock I am seeing it 1. That means on this clock it will be becoming 0 because of this statement. I will go to so-called the done state. That means I have finished sending the entire string. So I come to done state and I will remain in done state forever because I have completed everything. Now you have to declare things. So local param idle is dt0 and is dt1, done is dt2. And 3 state, that means we need 2 bits. So let's say reg 1 down to 0 state. Okay, we need a bracket here. Now the only thing that is missing for the protocol is the completion of handshaking. So remember, we make this signal high to indicate I want to send a valid data, and the other module will make this signal high to indicate he has finished sending. Okay, now if we are coming back to done state, that is fine, but when we are going back to idle state, okay, we need to wait until the signal becomes low, then only the protocol is completed. So you make this high. When the other module sees this signal is high, he sends data. Once he finishes sending data, he will make this signal high. When you see this signal high, you will make this signal low, and when the other module he sees this signal is low, he is supposed to make send done low. Okay, so you should send the next character only after this signal becomes low. So this completes our coding. Now you need to synthesize your design. After synthesizing, you need to do pin assignment for all the signals, clock reset, and all the OLED interface signals. You can find the pin locations from the Z user manual. I have already done it. This is how it should look like once you have done it. And after that, you can generate bitstream. Okay, once bitstream is generated, I have previously generated bitstream. You can program the device, and once you program, this is how you should see hello world. You may notice like some more pixels are white. It's because the GDRAM inside OLED, it will have some random values. The locations which are not written by you, it might be having some random values, so that's why some of the pixels are randomly high. But if you send a large string which covers all the pages, you will see only the strings are present there. Or if you wish, at the end of initialization here, you can make all the pixels low by writing 0 to all the locations inside GDRAM. Then only you can start accepting the real data from the top module. Okay, so that's if you wish. Now the only drawback, or one of the major drawbacks here, is if you want to display another string, you need to insert that string here, you need to specify the size here, then you have to go through the entire process of synthesis and implementation and bitstream generation. So you'll see like this is not very flexible. Pure hardware implementation, as I mentioned before, is not very flexible. Each time you want to do any modification, you have to go through all these steps. So one thing that we can do is we can convert this OLED controller into an IP format, and we may interface this IP with the ARM processor through the ASCII interface. then I can use software to send the required string to the OLED controller. So in that way, through hardware software co-design, I might be able to have a better design. I might be having more flexibility compared to pure hardware implementation. So in the next video, we will be converting whatever OLED controller we have written in Verilog into IP format, and we'll be interfacing it with the processor core. Thank you.